Hi there and welcome from Ventura, California to today's webinar, The Future of Farming, Unmanned Systems in Agriculture, Innovations in Land and Air, sponsored by Novotel, InsideGNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in educational webinars. I'm Lori Dearman with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the state-of-the-art and science in unmanned agricultural solutions. Now, we've invited you along with over 350 professionals from 47 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Before we get started, Richard Fisher, publisher at InsideGNSS and Unmanned Systems, would like to take a moment to welcome you and to introduce General James Poss, who will be moderating the main portion of today's webinar. So over to you, Richard.
Thanks, Lori. On behalf of the InsideGNSS and Inside Unmanned Systems team, including our editor Glenn Gibbons, managing editor Stan Goff, and myself, I extend a warm welcome to our international audience for today's web seminar. We're delighted you could join us. Before we begin, I just want to explain InsideGNSS's approach to our web seminars. We limit ourselves in the number of webinars that we offer each year in order to allow the time needed for preparations that ensure the high quality of the content and presentation by our panels of experts. And I believe that you'll find that today's event provides an excellent example of that approach. Now, I want to turn the webinar over to today's moderator, Major General James Poss. He's a 30-year U.S. Air Force veteran and was the Air Force's Senior Career Intelligence Officer at his transition from active service in November 2012. He's a leading expert on UAS, having helped design the U.S. Air Force's Remote Split Operations System for UAS control and the Distributed Common Ground Station for UAS intelligence. General Poss was the Executive Director of the FAA's Alliance for System Safety of UAS through Research Excellence. Currently, he is the CEO of ISR Ideas, an unmanned systems and cyber warfare consulting firm, and also a columnist for Inside Unmanned Systems magazine. And by the way, that was the short bio. General Poss, thank you for joining us for today's event.
Well, Rich, thank you so much for that overly generous, nice introduction there. And I got to tell you, I'm coming to you from the Golden, Mississippi Gulf Coast today. As many of you know, I'm a native Mississippian, and I wasn't sure how to take the invite here. I am an expert in unmanned aerial systems. I don't know too much about ground systems, but I'm hoping that you didn't assume that I knew everything about agriculture just because I'm from Mississippi. But as I got through this, I realized actually I did know a lot about agriculture, so there's a self-fulfilling prophecy there. Well, listen, we've got a fantastic panel for you today. We've got the experts evenly divided between unmanned aerial vehicles and unmanned ground vehicles, with some true world experts on precision navigation here, because it's so key to everything that we would possibly do in precision agriculture. Lori, I tell you what, I believe we've got a poll that we want to go into first, and we're going to be doing a series of these polls before and after each set of speakers, just to see what you guys think about the subject beforehand and then what you think about it afterwards. So can you bring up the next poll there, Lori?
Absolutely, I'd be happy to. And folks, coming up on your screen is that first poll. And our question for you is, why would you invest in agricultural UAS? And if you would select one of these options, the market is about to explode, technology is ready, it's the right thing to do. Precision ag is good for the environment. The tech and policies might not be there yet, but I want in. Or perhaps you're thinking, are you kidding me? There's no market there. So looks like our front runner there with 43% saying the market is about to explode, 33% feeling like it's the right thing to do, 23% saying the tech and the policies might not be there yet, but I want in, and just 1% feeling like there's no market there. General Poss, what do you think about these results?
Wow, that's pretty interesting. I'll be honest with you. I thought it was going to be on either end, that we'd have most of the folks saying that the market's about to explode, and then I really thought we'd have some more doubters on there, but You know, again, as a Mississippian who has 40% of the United States of America draining through our front yard in the Mississippi River, I am very happy that we got so many people picked up on the right thing to do, because precision agriculture is good for the environment. Anything that keeps insecticides, pesticides, fertilizer out of our nation's watershed is a good thing, and this is a good way to do that. So I'm impressed. Okay, all righty. So without further ado, let me get into my title, my speech, which I've decided to name our Garden Variety Drones for Real. And what I want to do here is maybe put a little bit of doubt on what you originally thought the market was, certainly for unmanned aerial vehicles and perhaps even for unmanned ground vehicles. But before we can really start the presentation, I want to frame it in cold hard terms and ask everybody, what is the reason behind garden drones? And as far as I'm concerned, there's one reason and one reason only, and that is to save money. But it's to save money if you're talking about in the actual agricultural production business, an industry that's got some of the thinnest cost margins in the world, and obviously the most climatically and geographically divergent industry in the world. So this is a tough market to begin with. It's even tougher when you've got to introduce something that is going to get into our nation's and the world's farms on the guise of saving money. Okay, well, let's go into the theory behind agricultural UAS, and a lot of this has to do with the entire theory of precision agriculture. So in other words, instead of doing stuff the old-fashioned way, which is you slather every soybean field with nitrates and herbicide and pesticide, whether it needs it or not, you introduce a modicum of precision in there, and you only fertilize the portions of the field that you need, or treat the portions of the field that are affected with insects, not the entire one. So the theory is that unmanned aerial systems, UAS, can increase yields and cut costs by providing improved crop prescriptions, which is going to be based on very frequent, highly accurate imagery that we flat out haven't had available until today. We've done some experiments with precision agriculture, and the imagery required for it has largely been with space-based systems, which just don't have the resolution, or with manned aircraft systems, which are just too expensive to take images frequently. The other theory behind UAS for agricultural applications is that they can replace pilots for agricultural applications missions, crop dusting, cutting risk and saving lives, and saving materials. And the statistics back me up on this. The most dangerous general aviation mission in the United States is agricultural applications, crop dusting. Okay, so how do you improve yields with unmanned vehicles? Well, you use a variety of sensors, and the basic sensors are listed here on the screen. So what I've got in the top right corner is a basic farmer's field. That's with electro-optical imagery, which is good for spotting crop damage, places where hailstorms have done damage, equipment faults in your watering systems, places where the hogs have broken into. The one below it is the most popular and most useful sensor for precision agriculture, which is just simple infrared. And that's used for assessing crop hydration, how it's growing. And the interesting thing I found out from working at Mississippi State is predicting insect infestation. Insects never go to the dying crops, they go to the ones that are growing best. So if you put the pesticide on the good growing crops, you stop the infestation before it starts. One that gets an awful lot of interest is hyperspectral. The human eye can only see in about 4 bands of color. Hyperspectral systems can see in hundreds of bands of color. And if you can see in hundreds of bands, you can come up with very precise signatures that indicate very precise types of conditions, different types of diseases, different types of insect activity, or even basic information like crop type. And finally is the one that doesn't get a lot of attention but can have a profound impact on precision agriculture, and that's LIDAR, laser space-based radar, for lack of a better term. LiDAR is extremely precise, particularly when getting elevation. It could get elevation down to within 3 centimeters on some systems, which is great for estimating drainage areas on your crops. It's great for figuring out if you've got the plants are standing up and growing like they should be, and it's really good for tree population. At Mississippi State, we did a LiDAR hyperspectral 3D model of a forest, and our young sophomore foresters were 95% accurate in their species count as compared to actual foresters that went out into the forest to count them. So pretty impressive. Well, here's part of the problems with what we're talking about. You can't just dump a bunch of pictures on farmers and expect them to do anything with it. The imagery has got to be processed, and it's got to be processed pretty quickly for most applications, less than 24 hours. Is what you've got to go from imagery to a crop prescription. A crop prescription is a geo-referenced production input, for where you want to put seeds, fertilizer, herbicides, pesticides for application only as needed and where it's needed for the most economic production. So essentially it's a machine-to-machine format that tells seeders and agricultural applicators, like I've got on the lower right, where to put the appropriate application on that map that I've got in the middle there. Now there is also a need for just flat-out geospatial imagery for mapping. The timelines are a lot less for that, but the precision is just as important for geospatial uses as it is for prescriptions. Here's some of the challenges. The first basic challenge is it requires fairly sophisticated, well-equipped customers. Most farmers in the United States don't engage in precision agriculture. They spray all the fields with everything that their crop consultants tell them to do. They spray the entire field. They don't buy the very sophisticated agricultural applicators or seeders that are required to do this. So there's only a percentage of farmers that use what's called variable rate production. The other problem is that at least for unmanned aerial systems, it's going to be very tough to make the timelines within the current small UAS rules. As I've covered before in some of my articles for Inside Unmanned, there's very difficult to make money when you can't fly beyond line of sight or be lost. The current rules require UAS pilots to fly within visual line of sight, which means they have to keep their drone within about 2 miles of where they are. So if you go in a place like the Mississippi Delta, richest farmland in America, it would take about 1,000 within visual line of sight under current rules drones to do that. If you just extend that to radio line of sight, which is from the drone to the horizon, you can cover the Mississippi Delta with 9 to 10 sorties. When you go beyond line of sight, you can cover the Mississippi Delta, Louisiana, Tennessee, Arkansas with a single mission if you need to. The other problem you have is when you're talking about agricultural areas, data link coverage is pretty spotty. I'm not going to mention the company, but that is one cell phone company's coverage of the Mississippi Delta, and the dark green is the only place that you can get data. So a couple of problems there. The other problem you have is that this is one area where size matters. Current rules restrict us to UAS 55 pounds or below. In the upper right-hand corner, I've got an air tractor 502B, which is a very popular crop duster. It carries 500 gallons of applicator material. That's 50 small UAS in just the capacity of the air tractor alone. The other problem you got is you get small cameras on small drones, which means more pictures equals more passes and more money and more time. Whereas you can see on the middle photo, that's a small UAS taking coverage of a single field. That's going to take quite a bit of time as compared to what you could do with, say, an MQ-1 Predator-sized aircraft, which could cover that in a single pass. The next problem is that manpower matters. As we used to say in the Air Force, one of our biggest problems was figuring out how to man or unmanned systems. Because under current rules, you have to have a single pilot flying a single aircraft. You can't have a single pilot flying multiple aircraft. That is very technologically doable. So you get a situation like you do in the lower right-hand corner where we have a Japanese farmer flying a agricultural applicator, and he's got to stay with the visual line of sight and just control that one aircraft. But the biggest problem we've got is that the cost margins are so low. If it only costs $15 to $20 per acre to spray insecticide with a aerial applicator, whatever you do in the drone market, you have to be cheaper than that. So you have to stop the farmer from spraying $20 worth of insecticide over the acre and maybe just spray it over half the acre. So if cost margins are so tough for agricultural production, are there other agricultural markets out there? And I'm going to say yes. The one I think is most promising is a crop insurance market. If you were watching the political drama last year, there was a lot of stuff about the 2016 Farm Bill, and the reason it was so contentious was because that was when America started to switch from paying subsidies to farmers, in other words, paying farmers not to grow cotton, to switching them to crop insurance. Well, once we get switched to crop insurance, they're going to require verification throughout the growing season to cut false claims. They're going to want to know, did you plant the acreage of soybean that you said you did, or did you plant corn? If you're going to claim hailstorm damage, show me where the damage was. Are you really experiencing a drought, or are you just not watering your crops enough? You know, a variety of stuff. So in other words, every American farm, once we go to a crop insurance market via subsidies, is going to need multiple images per year. The other one, and this is the big one, is cheap drone imagery plus improved weather forecasting is going to give folks the ability to control the commodities market. If we can just improve our weather forecasting, the drone imagery is already there. If you can do it, you will be able to seize the pork belly's future market on Wall Street and make billions of dollars. But again, the big issue with at least the aerial systems, as I see it, is no one makes money without beyond line of sight. No one makes money unless we can fly larger, more fuel-efficient UAVs that allow us to carry bigger sensors. And as we learned in the Air Force, it's tough to make money unless you apply enterprise imagery, storage, and interpretation. You can't have one pilot flying one drone, pulling out that SD card and handing it to one geospatial guy. You got to have numerous pilots flying numerous drones, and you got to have single geospatial guys working on dozens of farms at a time using an enterprise system. Ground systems, I got to admit, we've got some great speakers coming up that are experts. I am not, but my take on ground systems is they have similar disadvantages to the aerial systems. They require sophisticated, well-equipped customers that are willing to put money into this. They're very reliant on accurate data, accurate location and geospatial data. They've got the same issues with cost margins that aircraft do. Their advantages is you don't have to do quite as much talking with farmers to see the need behind ground robotics. I mean, I'd argue in Mississippi we've been doing it since Eli Whitney and his cotton gin. As a matter of fact, if you really look at the sophistication of some of these precision applicators out there, just driving the tractor and towing them through the field is the easy part. And then, of course, the big one is you don't have to deal with the FAA. As much as I know them, God help us if we had an FAA for ground systems. I don't know if we'd be able to leave the garage. So that's all I've got. And let me turn it over to our next speaker. Demos has been with us quite a bit here with Inside Unmanned and InsideGNSS. He's a professor in the Department of Aerospace Engineering and Mechanics at the University of Minnesota, the Twin Cities campus, where his research deals with PNT issues, precision navigation timing, related to small unmanned aerial vehicles. So Demos, over to you.
All right, thank you very much. All right, so continuing on with I guess the previous presentation, I'm going to focus on UAVs and precision agriculture, and I'm actually going to zoom in even a little bit more closer and just look at the PNT challenge, the precision navigation and timing challenge associated with using UAVs in precision agriculture. And to put things into context, I'm going to start out by just kind of giving a high-level picture of what precision agriculture is all about and how UAVs and eventually PNT fits into this. So as you see on the slide, precision agriculture involves multiple things. The UAV is just one part of it. It's a sensor platform that gathers data. There's data analytics that happens that's used to make decisions, which are in turn inform control actions, and then they eventually end up being applications or things that we do with with the crops in the field. So the PNT is one piece of information that goes into this entire loop, and its goodness, its accuracy, its quality is important because, again, it either helps or detracts from making economic sense of using UAVs in precision agriculture. So as I'll show in the next series of slides is that PNT accuracy and to some extent integrity are going to be key metrics that need to be improved or need to be looked at to make precision agriculture, UAV-based precision agriculture, economical and practical. So, to anchor this discussion, I'll just use one project that at least me and my group here have worked on, and it's looking at the problem of soybean and dealing with insects, pests that actually attack this. Here in Minnesota, we're the third largest producer of soy in the United States, and every year, on average, these soybean aphids can cause somewhere up to 40% of loss in yield. So coming up with a way of managing and dealing with these pests is actually an important challenge, and one of the problems, or one of the projects we worked on, was looking at how UAS can be used in helping on that problem. So as you can see in this figure here, this is a soybean leaf, and it's infested with a lot of these small soybean aphids, pretty small. So the way it's normally managed is someone goes out and scouts the field, and these fields, as I showed you on the previous slide, can be fairly large, so it takes a lot of time, but a person goes around looking for leaves or looking for evidence of infestation, and once that's found, then one of the standard ways of dealing with it is to apply pesticide uniformly. However, that is not a good way to deal with this because the infestation is not uniform. And when you do that, you're going to start creating unnecessary runoff. And as General Poss pointed out earlier when he started out the webinar, the less runoff we have, the better it is for the environment. And then lastly, when you go ahead and do uniform application, you could end up actually killing off other species out there that are actually natural aphid predators. So it's actually turns out to be somewhat counterproductive. So being able to target specific, I guess, infested leaves or plants and applying pesticide when needed, where needed, would be an efficient way to deal with these pests. So that's where UAS come in. So one way to do this is to image the soybean crops using different types of imaging systems and look at them in different bands of light, which show plant damage due to infestation, and then from there you could decide where to apply pesticides precisely. That aspect of what band of light to look at and what the response of different bands of light to different types of aphid stress or damage, that's not my area of expertise, or not what I'm going to talk about, but rather what I'm going to talk about is once you detect that, how to use that information to actually pinpoint where pesticides need to be applied. And that's where the PNT challenge or PNT aspect comes in. So what this figure shows here is just basically how this would work. So you'd have a UAS that's flying over a farm field. Each one of these points, it would take a snapshot of the crop below. And again, the imaging system would be something that is consistent with being able to detect the damage in the crop below, depending on what kind of damage one is looking or what kind of analysis one wants to do. And once the images are taken, then position coordinates have to be applied to that so that someone can make a decision later on how to deal with that particular issue down on the crop below. So this requires georeferencing or assigning position coordinates to each image that is collected from a UAV. So there are a lot of ways to do that, but one way that will speed up this process and make things somewhat economical is if you had the ability to do what's called direct georeferencing, and that's the ability to assign position coordinates to an image that's been collected from the UAS just by knowing the position and orientation of the UAS itself or the UAV itself, and maybe some information about a terrain database or something that allows you to estimate distance from the UAV to the ground below. Now, the problem with direct georeferencing, or the challenge rather, is that any sensor errors you have end up in what I'm calling here misalignment in images. So for example, if you look at the previous slide, I showed these images that were gathered by a UAS. When you go back to stitch the image together, and so you would be able to do some sort of analysis of it, if there are any sensor errors, the images would end up being misaligned as shown here. So once that happens, it's going to take increased processing time to straighten things out. Now the challenge here is that with most small UAS, the navigation, guidance, and control systems that are used on them use a IMU, and most of them, at least the ones that are available these days, use single frequency GNSS code phase. And it turns out, as I'll show you on some figures next, that is not accurate enough to be able to do direct georeferencing. RTK, real-time kinematic GPS or carrier phase GPS, can provide the requisite accuracy, but again, it's sensors and systems suitable for small UAS are in the process of starting to roll out and become available. But what do I mean by IMUs with single frequency GNSS and code phase are not enough? This slide shows some results from our work here. So what you see on the left is an image that was stitched together from multiple images collected on a small UAS that was using a IMU combined with single frequency code phase GNSS GPS solution. And as you can see, the stitching, I mean, at first blush it looks okay, but when you start looking at it closely, you'll notice that, for example, this straight road here does not appear straight, and all of this errors are due to the inability of the system to do direct georeferencing. Now, it doesn't mean that you can't do stitching. This figure shown here is actually a same image on the left, but after a post-process type of stitching of the image where information in addition to the UAV's position, the UAV's pose, other things were used to do it. So it's possible to do image stitching given the current state of positioning, navigation, and timing solution on small UAS, but it takes time, and if you can't turn around these images quickly after doing a survey, then that cuts into the economic advantage of using UAS in precision agriculture. So the ability to increase accuracy on low-cost navigation solutions used on small UAS is going to be a key challenge for precision agriculture. Again, just to show that what kind of performance would be required, what is shown here is the results of a basic covariance analysis that was done to show how different level of navigation systems on a small UAS would allow you to do direct georeferencing. What we have here is an image collected from a small UAS that's about, I think, about 200 feet above the ground. And what we're looking at is our ability to georeference images along this line across this snapshot. So first of all, the errors, well, georeferencing errors, are not going to be uniform. They're going to depend on where you are in the image. And with this line, horizontal line here, it corresponds to this diagonal line here. So what we see is that out at the edges of the image, the inaccuracy of georeferencing is going to be large, and in the middle it's going to be the smallest. And we see a low quality solution here, a medium quality solution, and a high quality solution. So the high quality solution is something that you would not find on the small flight control systems that you have on UAS today. The systems that you could find off the shelf today would fall more in that low quality solution. So there's some work needed to get from here to here before direct georeferencing becomes a practical tool for use in small UAS and precision agriculture. Again, if you had if you're willing to pay the money and have the size, weight, and power constraints on a small UAS, then these solutions do exist. But again, they are expensive and not quite ready for prime time yet on small UAS. Now, moving on to the second challenge, it's the integrity challenge with PNT, and again, it may not have been apparent from the last slides that I showed that the information about the UAV's state are going to be determined by fusing multiple sensors, and depending on what you're flying, where you're flying, and what you're doing, you could have a huge array of different sensors that are being considered for use in small UAS. And these days, the standard sensor fusion engine that's used on them is a Kalman filter or some of its variants. With these non-traditional sensors and non-traditional sensor integration schemes that are being looked at, things like deep learning, machine learning, then the challenge that comes up next is how do you prove reliability or integrity of your PNT solution that's being used to control and guide a UAS in the precision agriculture application. In particular, this becomes a key problem when you start looking at the beyond line of sight operations where the integrity requirements are going to be very stringent. So how to deal with that is going to be a big challenge going forward. Now, in the case of UAVs and precision agriculture, it's not, I guess the saving grace is that the required level of safety or integrity is not going to be the same level that most people that have maybe worked around with integrity in GNSS are familiar with, which would be shown at this upper corner here of this chart. What this chart shows is that the it's a different way of looking at of safety and certification, and it's basically looking at kinetic energy, meaning the amount of damage that a UAS could cause if its PNT system failed, versus the required level of reliability. So for aircraft that are large in size and weight, the reliability has to be high because a failure could cause a significant amount of damage. On the other hand, on small UAS, that may not be an issue. So the level of reliability required is going to depend on the size of the UAV and the operations that it's conducting, whether it's in populated areas or unpopulated areas. So even though these advanced sensor fusion schemes are going to be challenging to prove integrity or reliability with, the level of reliability or integrity required may not be as high as it is for manned aircraft that we're, I guess, more used to when we talk about integrity. But moving forward, being able to show that a PNT system used on a small UAS, particularly beyond line of sight operations, is going to be a challenge. So with that, I guess just the key points, UAS can potentially increase the efficiency of agriculture operations, and I just gave you one example of a problem that we looked at, which was the aphid management in soybeans. Accurate and reliable PNT is a key enabler for this. However, if we start looking at the economics, beyond line of sight operations are going to be, I guess, needed in the future, and for doing those, reliability or integrity of the PNT solution is going to be a key challenge that needs to be addressed and need to be dealt with. So with that, I will stop here and I will hand it over back to you, General Poss.
Oh, hey, thanks a bunch, Demos. I really appreciated that presentation. I learned a lot out of it. So, listen, I guess we're about halfway through the show here. So let's go ahead and take a break and answer some questions from the audience. So if my panelists are ready, I'm going to fire off some questions here, and we've got a couple of really good questions here. So Demos, if you feel up to it after just giving that wonderful presentation, I've got a question that deals with the advantages, disadvantages of satellite imagery versus drone imagery. So basically one of our audience members is asking, with all the advances in satellite imagery that we're seeing today, and we're seeing some fantastic increases in resolution, do we still need drone imagery, or is some of the resolution that we're getting off of the Sentinel-2, which will get 10-meter imagery every 5 days, isn't that enough for many applications in grain crops, or do you really need that ultra high fidelity imagery that you get from drones? So Demos?
Okay, I mean, I could say something about the motivation for using small UAS. I don't, and that does not mean that all these other advances in satellite imagery are not useful. But there are a couple of things that I guess would make UASs advantageous, and to be able to do that. One is when it comes to, I guess, weather. In the case of I guess instances where you're not able to get satellite imagery, you might be able to still fly UAS. And the second one is the quick turnaround. I mean, the eventual, I guess the goal that, or some of the model that is being looked at, is having the ability for any farmer to basically launch one of these things on their own and get instantaneous or quick feedback on the state of their crop. So, and I'm not sure that the satellite imagery is at that point just yet. So those are two reasons why the UAV aspect would be useful and why it would be an economical one to pursue.
Okay, great answer. Yeah, from my aspect of working with precision agriculture in Mississippi State, I do think resolution does matter. And the resolution that you get off of small UAS is just incredible. For the intelligence geeks out there, NIRS 8 or 9 imagery is routine with these type of systems. This you get into is particularly with hyperspectral and some of the IR systems is being closer to your target, flying slower, flying under the weather, as Demos mentioned, has a huge impact. And yes, there are quite a few targets where you need sub 1 meter and sometimes sub half a meter resolution to really get the effect that you need out of that. So hopefully we got that one. Okay, next question I'm not going to be able to squirm out of. I'm going to give to myself, and this is a question I get pretty frequently, so frequently that I wrote an article on it this month on Inside Unmanned, and that is, how far off do you think it's going to be before the FAA approves beyond line of sight operations? And if you have a subscription to Inside Unmanned, you'll know the answer in great detail, but basically, I always tell people it's a minimum of 3 years and probably more like 5 years out. If you look at how the FAA has to do aviation rulemaking, and it's a purposely slow process because of the safety concerns, it's going to take it a minimum of 3 years to do any type of aviation rulemaking from start to finish. I think the other two variables we've got here is, one is technical, and there's a couple big technical changes that that we've been using in the Air Force since 1997. But the key is getting the same procedures that the military uses, say, for civilian operation, and that's number one. How do we provide detect and avoid capabilities for drones that are equivalent to manned aircraft? There's a bunch of technical solutions out there. Most of them are very, very safe, but getting that proved for commercial ops is a big deal. The other one is, if you're going to fly beyond line of sight, how are you going to reliably extend the data link without using expensive satellites or with getting cheaper satellites? The Air Force can fly Predators from 6,000 miles away because we can afford to outbid CNN for satellite transponders over Southwest Asia. Not everybody can do that. And then the final one behind my relative pessimism is the fact that the FAA is going to go another reorganization path right now, and that's probably going to lead to further delays. So 3 to 5 years is what I'm saying. Okay, well, I think that's all the time we have for questions. So I tell you what, Lori, I think you got another poll teed up so you can see where we're going. All righty.
I sure do. And question is, what's stopping you from investing in agricultural UAS? And this time you can select all that apply. Is it that the FAA rules are too restrictive? Perhaps technology just isn't there yet? There's no market. The cost margins are too tight. Maybe you're thinking, are you kidding me? I'm investing now. Or maybe it's something else. All right, got 36% citing the FAA rules are too restrictive. 28% technology just isn't there yet. 27% no market. Cost margins are too tight. 13% investing now. And 19% coming in with other. We do have a few of those other comments coming through. Thank you for that input. And General Poss, any thoughts here on these responses?
Yeah, I kind of thought that most folks would put down that the FAA rules are too restrictive. I'm not sure if I agree with everyone saying that technology just isn't there. I think it's there within the next year to 18 months, and we'll discuss that a little bit further with some of our other speakers, particularly when we talk about precision location. The cost market, I can kind of identify with you. Until we can see some figures on what it's going to take to fly beyond line of sight, I sort of identify with you, certainly for the agricultural production side. I'm not sure if I agree on the crop insurance and the commodities market side, but interesting spread there. So, all right, now that we got that over, we're going to move into our next speaker, and we're really lucky to have Mel Torrey, who is the CEO and founder of Autonomous Solutions Incorporated, or ASI, which focuses on the development of autonomous ground vehicles in markets like mining, construction, material handling, security, and agriculture. He is a real expert in an area that I'm not, and that's autonomous ground vehicles. So over to you, Mel.
Thank you, General Paz. It's an honor to be involved today. ASI was founded about 17 years ago, and we have been fielding robotic solutions across all of the industrial applications. And so you see some examples here: material handling, moving boxes around factories, those kinds of things. You can see in the right, we've done some agriculture, some security, some cleaning, some mining, and even automotive. And so the goal being, can we move the productivity enhancements that we've been able to get in the factory environment out to these unstructured environments like farming? Agriculture was our initial market. We actually started back in 1995, 22 years ago, doing multi-vehicle spraying missions for the Department of Energy with a dual-use application of spraying potato fields up in Idaho with the Department of Energy's INL lab. And as John Deere saw some of the results there, they kicked off an autonomy program with our university, Utah State, and then we founded a company in 2000 to start to productize these kinds of solutions. And so, as you've seen, a variety of different concepts in orchard, vineyard, wide acre, and then, as some of you may have seen, the concept tractor with CNH Industrial, kind of the state of the art today and showing what's possible and where we're at. So in moving forward in this market, what are some of the drivers? What's really motivating the funding, the drive from the end users, the farmers? The first one, as expected, is really the step change in labor costs. We are having some significant minimum wage hikes voted in across both the United States and in Europe, and these are significant step changes, and so there's a lot of concern. Some farms are seeing up to a 20% cost increase for operating, because when a $10 an hour guy wants a raise, so does the $20 an hour, so does the $30 an hour, and so all of the wages step up. The availability of the labor and having the right skill sets. So the youth are not staying on the farms much anymore, and the recent immigration reform is causing a lot of concern. The pending wall in the United States is motivating a lot of fact-finding, understanding what's possible for options, because they just cannot get the labor, and farms are staying unharvested actually in the fall. So we've got to make some changes there, and then the right skill levels. The equipment's getting more and more expensive, and so if you're bringing in new people, the potential for equipment damage is significant. Maintenance savings. This is kind of an exciting one. It's harder to measure, but we are seeing, for example, one application that we have out there is mining, where we are seeing 3 times the tire life for an autonomous mining truck. If you look at once you drive a vehicle perfectly, meaning according to the OEM specification for that tractor, you can see significant improvements in the performance and life of the tractor, the implements, etc. We've also seen that over 50% of the cost of maintenance is air conditioning. And so as you take the people out of those applications, you can significantly reduce your downtime and the amount you're spending there. Productivity is also a very exciting one, and you can do some math around this, and there's more and more studies being done to help us understand the true impacts. But as you look at how can you optimize the coverage of a farm, the implement paths, the size of the equipment, should I get 20 foot, should I get 60 foot, should I get 80 foot sprayers, those kinds of things, what are the trade-offs, and then the number of units. If I use 3 versus 5, what's the impact on time, what's the impact on compaction, and there's a lot of great studies being done on the impact of compaction on yield, and then fuel and cost, choosing those priorities, prioritizing them, and then being able to run our optimizers to tell you, comparing 2 scenarios or just optimizing given a couple of options. Another exciting change that we're seeing is farmers are starting to ask the question, what is the right size? I've been pushing, going bigger and bigger. I have difficulty in transportation moving on these public roads, and the costs are significant, and when I lose one large combine, the impact is significant. As we start to ask that question when labor is no longer involved, you can do a new math. The equation has changed, and now smaller vehicles and more of them can make sense. Compaction is definitely affected. Fuel, service, downtime. If you lose 1 out of 10 little tractors versus 1 out of 3 monster tractors, the impact to your end game is significant. And then, of course, transporting these pieces of equipment on public roads. So we're seeing smaller machines, less service and support, fewer total units. So if you're running them optimally, if you could have gotten away with 5 units in the past with humans driving, perhaps with optimizations you can get down to 4 and not have to have that spare tractor sitting there. And we're also seeing that some of these smaller tractor OEMs are getting excited because of this new math and their ability to come in and disrupt and displace some of these larger tractor manufacturers. So one of the challenges of moving this forward, I'll talk through 6 today briefly. I'll leave the positioning more to Ben, our next speaker, but vehicle automation, the challenge of having a reliable vehicle automation that can do all of the functions that a human usually helps with, communication, getting the message out to the vehicles and information back, perception. How do I, as an autonomous vehicle, see through the weather, the snow, the rain, the dust is especially difficult, and then foliage. How do I see through a cornfield and see that there might be somebody there, an animal there? And then positioning. Obviously, as we have blockage and consistency concerns, how do we make sure we always know where the vehicles are at? Serviceability. As we increase the complexities of adding radio networks and multiple computers, how do we make sure that we can figure out what's wrong and fix it? And then 6, liability, which I've been surprised by has been more of a significant roadblock than all of the others combined. So first one, automation. Exciting thing is that the large vehicles are making great inroads towards drive-by-wire functionality, meaning they can be controlled electronically. You don't have to have a big actuator, motor pushing on a brake pedal. You can actually electronically trigger that. And this is really being pushed forward through CAN bus messaging. One of the very exciting and I think industry worldwide leading innovation is a message set called the ISOBUS Class 3, which allows for us to control all of the functionality of the tractor through a CAN bus message, and that it would be adopted across the industry so that a case tractor could be controlled by a John Deere implement and vice versa. So the moving forward of a standard that provides a common language for us to control the equipment will allow for this technology to really take off. So great steps forward in automation. Communication advances. The challenge of seeing far enough and talking to these vehicles is that some frequencies are blocked, and we only have a couple of public frequencies. So as we look at the multi-frequency solutions that are coming online, this Ragent radio, for example, has 3 public frequency bands, and so if the trees are blocking a certain frequency, perhaps you're getting more throughput with a 2.4 gigahertz band, that kind of thing. Telematics, we are seeing this being offered pretty well on every line of equipment out there, and so they're pushing for better connectivity so that they can talk to the equipment, understand where it's at, and yield type information and service information coming from there. So they're pushing the radio network coverage forward, and then some very exciting things coming. And what we're seeing is 1 gigabit bandwidth coming within, even at the end of this year, there will be prototypes out there with certain networks, and then full coverage in many locations in 2018 with 5G, the cellular, and then a huge push right now for companies. I show a link there for SpaceX, but there's 2 different groups putting out low Earth orbit satellites that will provide worldwide coverage of 1 gigabit per second kind of bandwidth with very low latency, meaning we can get messages quick. We could actually take over control of vehicles anywhere in the world and actually control them remotely with a remote control joystick, for example. Sensor cost, huge support coming from the automotive industry moving this forward. We've talked about LiDAR today. That's moving to solid state, meaning instead of moving parts, we are getting a chip-based solution that drops the cost by at least an order of magnitude. So as you see there, Quanergy putting out a $250 LiDAR, and we're seeing the same innovation coming in radar, and then processing power-wise, parallel GPUs are taking the analysis and analytics to a whole nother level. Service and support. This is going to be challenges, I mentioned. This complexity is high. You've got a lot of radio networks out there, IT type staff needing to maintain that currently. As I said, telematics is pushing the coverage. Functionally, we're getting more information off of the equipment so we can understand what is wrong, what is that vehicle experiencing, is it, how is its yield, is it experiencing overheating, those kinds of things. And then as I show some of the future here, in the top right you see a robot actually refueling. It's connecting up pipes. Where we see this going is that robots will be able to help. Initially, we see that the maintenance technicians that are currently in place at our dealerships can be guided, and so you see in the bottom left using headsets. So now there's a headband that you can put on that provides vision for the service technician. He can be guided by others or be provided with on-screen support and guidance in how to change an oil filter, things like that. So where we have low-skilled technicians around the world, we'll be able to provide real-time support for them in doing their job. And then ultimately, like we're pushing in mining, we'll be refueling and servicing equipment as it's actually driving. Liability. As I said, that's been the biggest. People disable safety systems every year. That really surprised us, that farmers are disabling safety shields and hurting themselves, and then the OEMs are settling out of court to avoid the bad publicity. And so millions and millions of dollars are being spent on this. And so as we've gone to move to market, we've had those kinds of questions like, this is how many millions of dollars we expect in lawsuits. Can your profits sustain the product despite those kinds of expected expenses? So our lessons learned are we need to design tamper-proof systems so that these safeties can't be disabled. We need to get a good insurance, and we are working with insurance companies, and we are insuring our current solutions. And we need to support best practice standards. As we look at the standard space out there, the functional safety, and how do we make sure that we are leveraging best practices, that we're all following those, so that we assure that we don't have a bad accident that really puts us all back, that keeps us from moving forward in the aggressive way that we are currently. The new one that's, it's been going for quite a few years actually, but it's really getting traction now as drafts are coming forward, is the highly automated agricultural machines standard. We're members of that, all the major OEMs are, and that is moving these best practices and getting an agreement on what those are so that we can get a foundational piece for litigation and just best practices for all of us to follow. So great progress there. And then another neat trend is that we've seen in automotive that once one OEM has come out and taken the responsibility for any future liability concerns, that others have followed suit. And some of those companies have actually also had shares or ownership in ag companies. So we see this continuing. We see that these larger companies are willing to take the risk. They see the advantages and they're moving forward. And so as an industry, others will come on board. So one final caution on the liability, some of the lessons that we've learned in the field that I think is important to share, is it's a slippery slope as we look at people getting comfortable with the technology. Share one story. This is an example, and this isn't an actual picture, but we had someone out doing service and support, and we had some autonomous mining trucks driving around, and They went onto a road they weren't supposed to. They took a cell phone call and decided to stop and talk to the person. And we heard them bragging to another neighboring mine about the performance of these autonomous vehicles, and they told this story that I was sitting there talking on the phone, and I all of a sudden was surrounded by dust and realized in my rearview mirror that an autonomous mining truck had stopped, and that he thought it was pretty cool. We found that people just get far too comfortable and start to just take for granted that these vehicles are safe and performed 100% and trust them far more than we would as developers. And then we found they stopped monitoring them. We automated a bunch of tractors for a large tire manufacturer, and so they would run and test these tires to make sure that they would last the years that they were being rated, the miles they were being rated. And we went to see how it was going. Turns out that they turned out the lights at the end of the day and went home and left these 30,000-pound tractors driving around. And so that was quite a shock to us. We realized that they would just come back in the morning, refuel them, hit resume, and the tractors would go back to their job. That was not the design purpose, and so very concerning there. We've got to be more careful about what we put in place to assure that people are still in contact. And then finally, taunting them. We've seen farmers show other farmers how their autonomous vehicles are running, and then actually jump out in front of them and show how the obstacle detection and avoidance worked. That's terrifying. You would never do that with your son driving with his cell phone. Why are we doing it with a robot? So where are we at? It's very exciting. We're finally at the place where the cost and the maturity is ready to field, and this year we're actually fielding with hands off, meaning we are no longer running these systems, we're no longer monitoring them. So exciting times for the ground side. Back to you, General Poss.
All right, Mel, thank you very much. So, Lori, we're back again. Time for another poll, and I think this one is going to be a little bit more specific. We're going to be asking you to reach into your pockets. So you're ready with the poll?
I sure am. There it is on the screen. What incremental cost would you expect to pay for a fully autonomous piece of ag equipment? And this is per unit. So an incremental cost of 10K, 35K, 65K, or 100K. Looks like 27% of us in that 10K range, 42% in the 35K range, 14% in the 65K range, and 18% in the 100K plus range. General Poss?
All right, well, thanks. You folks just set the price for agricultural autonomy, and it's somewhere between 35 and 10K, so congratulations. Nah, that's about what I expected. You know, I tell you what, you know, particularly if you go even with 35K, you just look at the savings you're going to get off of a single year, and that's a pretty good payback. It's amazing. We now have Ben Schilling coming up, and Ben Schilling is the Director of Sales at Novotel Incorporated and is responsible for managing the company's global agriculture business. He has spent the past 15 years in various sections within the precision ag industry. So Ben, over to you.
Thank you, General Poss. For those of you who are not yet familiar with Novotel, we design, manufacture high-precision GNSS positioning technology, and we're based here in Calgary, Canada, where today it is a sunny minus 15 degrees Celsius. We've been providing global positioning solutions that meet the accuracy and reliability requirements of our land, air, and sea customers for over 20 years now, and are the market leader in our space with more than 50% market share. Novotel's market segments can be categorized into two groups, measuring and guiding, and historically we've been strong in the survey, timing, construction, ground reference, and agricultural markets. In more recent years, we've been growing in the autonomous and unmanned systems. Novotel follows a true OEM business model. As a supplier of our technologies, we provide the position, navigation, and time data to system integrators that are incorporating our products into their solutions to sell into their markets. A couple examples here are into autopilot systems for autonomous aircraft, into agricultural guidance systems for farm machinery, and into dynamic positioning systems for offshore vessels. What trends are Novotel seeing in GNSS positioning? In the early 90s, late 90s and 2000s, it was more about positioning accuracies, positioning techniques, and multipath mitigation. The phase we're in now is more about robustness and reliability of those positions, multi-constellation, sensor fusion, position plus orientation. And in the future, where Novotel sees that going is more of a focus on safety of life applications and functional safety, so as well as integrity, so validating those positions that we're reporting. What is Novotel doing to address these trends? Our competitive advantage comes from unlocking the precision and reliability in positioning by mitigating GNSS limitations and authentication. And in the real world, that allows us to solve problems like jamming, lack of availability, and spoofing, which are all critical to autonomous applications. We offer our span technologies using GNSS plus INS, multi-constellation GNSS receivers, and our interference toolkit, all to aid in assuring that you get position and navigation data in GNSS denied environments, regardless of the cause. How is Novotel situated to solve these challenges in the precision ag market? We have a long history in OEM precision agriculture. We've been supporting our customers now for a little over 17 years. As you can see, we started with the first generation semi-autonomous auto steering systems all the way back in 1999, and are continuing today with our newest OEM 7 cards, smart antennas, and TerraStar correction services. Our customers are relying on Novotel real-time technology and features such as Glide, SteadyLine, and RTK, as well as our centimeter level accuracy TerraStar C and decimeter level accuracy TerraStar L correction solutions. In addition to the real-time positions, though, we also provide high accuracy post-processed position solutions for use in survey, ground and aerial mapping, and photogrammetry from our Waypoint products groups, as Demos was talking about a little earlier. What are some of the trends that we're seeing in autonomous land and air and precision ag? As an OEM provider into these integrators, we're seeing them follow a similar trend line that we saw with our semi-autonomous non-ag land and air and larger aerospace solution integrators. The focus is on increased sensor fusion, system accuracy and robustness, and focusing on reducing size, weight, power, and cost of these solutions. How is Novotel doing that? Providing dual frequency RTK and PPP solutions, multi-constellation functionality, TerraStar corrections, dual antenna heading solutions. We've seen a big uptick in that product demand. Span tightly coupled GNSS and INS, again for use in autopilot systems and with LiDAR and photographic sensors, as well as our post-processing software packages to provide the highest levels of accuracy that the integrators can get. And what is this enabling for our customers? We've seen UAV companies launching various levels of service based on accuracies. The trends of these services being offered from 2D and 3D map processing, vegetation indexing, plant height, canopy cover, all of these are requiring more accuracy and more robustness. We're also seeing increased use of UAVs for spraying application for small fields and hard to access crops. And a lot of these integrators had started out with single frequency L1 or L1 RTK and just found that they were generally not as reliable or robust enough for the solutions they're trying to provide. Demos mentioned as well that the misalignment or loss of position equals increased time and costs for these integrators. So we're using combinations of the higher accuracy solutions in order to make better use of the data being collected by the other sensors on the vehicle. So as the breadth of these applications becomes greater, the need for more reliability and robustness is growing to meet the needs of these new applications. And Novotel's vision for unmanned land and air is assured positioning anywhere. In our ideal view of the future, position, velocity, and attitude are all solved in every application, in every environment, all the time. And this to an appropriate level of accuracy and with a high level of integrity. Back to you, General Voss.
All right, Ben, thank you very much. Okay, and we got to go to the next slide here, which was going to show where you can get the PDF of the presentations, which will hopefully be up here right after the show. And as you can see below, we've got the email addresses for all of our panelists, and we've talked about it beforehand. Please don't hesitate to email us if you've got additional questions that we didn't cover here during the panel itself. Okay, all right, so I think, Lori, we're ready for our fourth and final poll. Over to you.
Yeah, in fact we are. That last poll, what are the big obstacles with agricultural UAS as you see it? So can't fly beyond visual line of sight yet, so no money in visual line of sight. Technology isn't there yet to provide timely ag data. Cost margins are too tight. 55 pounds is too small for an ag UAS. Or maybe you have something else in mind. All right, front runner here with 47%. Can't fly beyond visual line of sight yet. 20% saying technology isn't there yet to provide timely ag data. 43% cost margins are too tight. 32% 55 pounds is too small for an ag UAS. We have 14% weighing in with other. So General Pass, how do these look to you?
You know, I tell you what, I finally got it right on the fourth poll. This is about what I would have expected to see. I'm not sure if I agree that the technology isn't there. And again, I think we got about a year, maybe 18 months before we solve nearly all of the problems from a technological side, not a policy side on this. So very good. Okay, Lori, so thanks for the help with the questions. I guess we're coming up to our my favorite part here, which is where our final question session with the experts, and we've got some great questions here. All right, first and foremost, and I get this one a lot, and I'm going to go ahead and put this up to both Ben and Mel, if you wouldn't mind. How do you tell if your robot, your autonomous vehicle, is being jammed, which you really know it does? Jammed, I'm assuming they mean either the data link or the GPS receiver. So how do you know if your robot's really where it thinks it is? And Ben, if you can answer first.
Yep, I'll jump in and take that. A part of what you'll see is just, I think, loss of control in the vehicle if you're being jammed. Is one of the main things. One of the things that Novatel's just come out with specifically to work with jamming and spoofing is our interference toolkit, and this is a product that can help detect jamming and spoofing. So from an end customer standpoint, if they're starting to see anomalies, they wouldn't necessarily be able to do anything about it, but contacting their integrator that would use our interference toolkit will help them solve those challenges.
Oh, great. Mel, do you have any thoughts on the question as well?
Yeah, I think so. I think it's definitely a concern. We have a lot of redundant safety in place to make sure that we are maintaining control. We call them heartbeats to make sure that we're getting messages to and from the vehicles. And then if the vehicle leaves the path, if anyone's telling it to leave the path, we have a tolerance around that where we would alert the operators that something's wrong. We can automatically trigger a stop or call the operator and let him know. Also GPS boundaries, so worst case is it leaving the area where we have specified. That would give us an alert. So I think it's much harder to tell if someone's stealing your data, if they're listening in and learning from your system, getting your data. That's much harder, and I wouldn't say that we are there with a price point for the encryption to make sure that our data is safe. But as far as someone taking over the equipment, I think we're pretty safe there.
Wow, that's a great answer, and that's the first time I'd heard about the concept of heartbeat. That's a great idea. Okay, I'm going to keep you on the list here, Mel. Another one that we've got is when you're talking about making autonomous ground vehicles, can you do it just with GPS, or do you need other sensors? And Ben, if you feel like jumping in after Mel's done, I'd be interested in your thoughts on that as well.
Absolutely.
Yeah, great question. I think the functional safety guidelines in ISO talks through a risk analysis. So you look through all of the possible things that could happen. If you can cover those costs, those risks with things like barrier fences and keep the people out or the animals out, then I think you can. If your risks tell you, no, there are birds that can fly in, they can get under the fences, to have that redundancy and that functional safety, you may have to add additional sensors to make sure that you can keep that vehicle safe.
Okay, sounds good. Ben, what do you
Yeah, I would absolutely agree with Mel. I think, using GPS only, yes, it can be done, but it's more of a question of, do you really want to do that? And I think for fully autonomous, you really need multi-constellation GNSS combined with the mesh of other sensors that complement each other, and this is providing the redundancy and integrity that you need, especially if you're in sensitive areas or there's people or other things around, as Mel was mentioning.
Can I pipe in here and say a little bit about
sure.
the UAV side of the things? In the case of UAS, though, it will be very difficult to just have GPS alone to give you all the state information you need about the vehicle, particularly when you start talking about attitude and orientation. I guess you could potentially do it with multiple GPS antennas, but wouldn't be robust when you're doing turns and banks and things like that. So other sensors are not only good from a safety and redundancy point of view, they're also required to be able to generate a complete state picture of the vehicle, like inertial sensors, particularly is what I'm thinking of.
Oh, that's a great point. Okay. Hey, and just real quick, I've got a one-on-one for Robert, who's dialing in all the way from Uganda. He's asking how people like himself in Uganda can get UAVs for use in Africa. Robert, I'll tell you what, go ahead and email me, and I'll help you out with that. I got great support from the Ugandan Armed Forces when I was active duty in the Air Force, and I'd be more than happy to help you with that one. Okay, all right. Here's another one, Mel. I'm gonna keep torturing you here. So, do you see partial autonomy as a use case, or is full autonomy the only way to go? Is there a midway point?
Great question. I was in Australia a couple of years ago looking at an almond orchard, and they had their tractors lined up in the yard, and they were installing satellite dishes in each one to give the operators something to do because they were losing their staff because they were getting bored. So those vehicles largely are doing semi-autonomous type functionality. They're driving to paths, straight curves. They are handling implement operations at the end of the turn. So I think ag has been the leader as I tried to bring some of that functionality into mining. Ag has provided the example. So I think there's some great examples of basic functionality that is there already. As I met with a mining executive last week, he said, labor's not an issue in Africa. I just need these vehicles to run optimally, meaning I do it the how right, and I'm running them within their desired thresholds of speed and that kind of stuff. So I think where you have labor shortages, then full autonomy is going to be pushed much faster. Where labor isn't an issue, availability or skill level, then I do see that you could put someone in the cab still. They're providing that safety observation, but you have that farm as being run as efficiently as possible. The vehicles are following the paths that are optimal. John Deere saw about a 10% increase in running an orchard operation autonomously versus how the humans do it. So if that 10% is enough for you, then that's a great approach. And then just driving that vehicle according to spec so that you lower your maintenance costs. I think those two wins are big enough in these third world countries for sure to run a semi-autonomous operation where the vehicle's pretty well doing everything, but the human is providing oversight.
All right, great answer. Demos. Here we're going to go back to unmanned aerial systems. Got a question about how you can quantify how long, in terms of manpower and whatnot, it is to process raw image data that specifically in the Aphid example that you put out there. How long does it take to process the data, correct for geolocation errors, and what's a rough estimate for the amount of manpower it takes?
Well, it depends. It depends on the size of the field, the size, the rate at which you took pictures, etc. But in the small examples we've done, it could be on the order of tens of 20 of minutes to it could be, again, for the larger fields, could be up past an hour. However, if you could imagine a actual business case where this is going, it's not going to be a single field that the person, whoever's processing, is going to have to do. They're going to have to do large fields, perhaps multiple fields. So it could be a challenge to get a quick turnaround on a really large field, high resolution imagery taken from a UAV.
All right, that's a good one. Yeah, and I know from my experience with the sheriff of Mississippi State, a lot of it's got to do with the promise of auto populating signatures to detect various conditions that the crops are in. And if you work with signatures, which is harder than it sounds, it really does cut down on the manpower that you've got. Okay, here's another one, and I tell you, I'm gonna pick on Mel first, but I think Demos and Ben and even myself will get in on this one. It's another one that we get quite a bit. What about robotic collaboration between aerial and ground vehicles? Is anyone looking into that? Is that useful? What do you think, Mel?
Oh, I definitely think there's huge potential here. I think what Demos talk about with the time lag, that means we're going to use the data, but it may not be real-time collaboration, meaning we've done the analysis and now we direct these ground vehicles to do some of this higher capacity type spraying based on the high fidelity information we're getting from the aircraft. I think that is real, and that is now. That's this year we need to be doing that. I think as you look at real-time, where the vehicles are dynamically being tasked and positioned and warned about obstacles or safety risks, I think that's down the road a bit as we increase our processing speed, can leverage the cloud perhaps for some of that off-board processing. We'll be getting to that stage, but I'm sure it will happen.
Okay, great answer. Demos, Ben, you guys have any thought on that, Ben?
I guess from our perspective, I think Mel's right. I think we'll see that a little bit more in ag in the coming years. We're seeing it in offshore right now. We use a product called Align, and we'll have technology on an autonomous helicopter, for example, as well as on an offshore vessel, and we can autonomously land and take off with that helicopter, all while the vessel's moving, including pitch, yaw, roll, and heave. So it's just a matter of transferring that technology to the proper cost point and a few other things to get it into an ag environment. But from a big picture, that technology's there, and it'll take a little bit of time to move it into the ag space.
Sounds good. Okay. I've got another one, and I'll split this one with you, Demos. Kind of in the example I used before of 1,000 visual line of sight sorties, versus one beyond line of sight sortie for an unmanned system to cover the Mississippi Delta. One of our listeners is asking a very good question. Then, well, if BLOS is so efficient and you can't fly drones beyond line of sight, why not just use a manned platform to collect large area data? Like that. What are your thoughts on that, Demos? Is that going to get you the imagery that you need from a manned platform versus a drone?
I mean, that's what's being done. I mean, manned aircraft are used for collecting the images, but the issue is, can we do it more economically and more safely? I mean, you pointed out one of the risky operations. I guess it's not imagery, it's crop dusting, but in general, when you have a manned aircraft flying, there's the issue of cost and there's the issue of safety. So UAS are, I guess, potentially poised to be able to cut down the cost and increase safety in doing these operations. So yes, I mean, we're doing it with manned aircraft, but we could do it more efficiently if we could do it beyond line of sight with UAS. At least that's the way I see it.
Yeah, and I got to say that's basically the answer we came to in the U.S. Air Force, is the fact that you may not save manpower. You may save manpower depending on whether you're allowed to fly multiple vehicles with a single platform or not. The key thing is that drones, by definition, are easily connected to an enterprise level system, because you have to constantly communicate with a drone via data link. That makes it dead easy to then take that imagery, move it into an enterprise storage system, move it into an enterprise interpretation system. That's a lot cheaper. You got the fact that you may be able to fly it more efficiently with your air crew. But the big thing we learned in the Air Force is the huge difference in endurance between manned and unmanned platforms. U-2, on a good day, you really want to torture the pilot. You can fly him for about 10 hours in a spacesuit. Global Hawk, I think the record is 32 hours. So you get a lot more efficiency out of not just the manpower equation, but the pilots as well when you're doing that. Okay. So I think have we got time for one last question, Lori, or did I just take too long?
I think we have time for one last question.
All right, one last question. We've kind of danced around it quite a bit, but Ben, I wonder if you could address the challenges. Why is it so hard to build RTK receivers for small UAVs? That seems like that would be pretty simple to me.
Yeah, it's it's not as much the challenge of building them. It's getting the right size, weight, the receivers, antennas, INS, and communications all onto the UAV. It's kind of size dependent, more on the UAV than anything. So it's one of the things we're focusing on, is how can we package things smaller and at the same time get that at an appropriate cost for some of those technologies to try and get everything on there. Especially when you look at dual antenna solutions, for example. You know, ideally you want those antennas about 1 meter apart. 50 centimeters is adequate. It'll work for UAVs, but again, you need the right size of UAV to get there. So I think size and weight is really where the challenge is, and that's those types of things are what's being worked on and what we'll start to see in the next few years. But I also think that some of the UAV in general will start to get bigger, or they'll start to use larger UAVs for a lot of the applications, so that part of that will kind of sort itself out.
Yeah, same thing in the Air Force. A lot of times you forget how much actual real estate you need on the aircraft, not just to mount the antennas, the further their perfect length apart, but just to get enough grounding, particularly when you're building aircraft out of composites. Sometimes it's difficult to ground all those electronics without a decent sized base, so good stuff. All right, go ahead.
Sorry, one other thing to add too, on the smaller UAVs, it's also power consumption is a challenge. So we're trying to, even if you get, we're able to make some of the components smaller, the other challenge then again is power draw and power supply to those components, which you know, a larger UAV will have a larger payload, a larger power supply, and will help again kind of sort that problem itself.
Oh, absolutely. Most expensive thing in the aerospace industry is size, weight, and power, and you don't get a waiver for it. So, all right, I am officially getting the hook from Lori. It is time to wrap this up. I just wanted to thank Richard for setting this up, Lori for doing such a fantastic job, you and your partners out there. Demos, really appreciate everything you said about unmanned aerial vehicles. Mel, boy, I learned a lot about autonomous ground vehicles there. Wow, what an interesting area. And Ben, always an honor and pleasure dealing with you and looking at some of the challenges of precision navigation and timing, which is very underappreciated in this internet-based economy that we've been living in for the past decade or so. So Lori, I'm going to go ahead and turn it over to you and close this up.
All right. Well, thank you, General Poss. And folks, before we do sign off, thank you to each of you for joining us, and trust that you found today to be of value. Just echoing the special thanks to our distinguished panel members and, of course, our sponsor, Novatel, and our co-hosts, InsideGNSS and Inside Unmanned Systems. And again, thanks for joining. This is Lori Dearman saying hope we see you on the next one. Have a great rest of the week. Bye.